Hello, everyone. This is Akshay, one of your TFs. I'm going to be going over a little bit of ANOVA and how to use a calculator when performing the ANOVA test. Uh, just some background on ANOVA. ANOVA is used to check different populations and whether they are different from each other, if at least one is different from the others. For example, if you're trying to test processes in a manufacturing plant and they are different in price, but then they are also different in maybe quality, you want to justify the change in price versus that change in quality. So if that change in quality when that process is that much different, then it's worth the price, things like that. So the first thing I'm going to go over are the equations that you need to know and how to visualize the graphs and um, or the tables that you see in ANOVA. So the first thing is going to be looking at the tables. So you'll have treatments or processes. Those are going to be your different process for manufacturing a gear or something like that. Uh, we call those I. So the number of treatments is I, capital I. And then we have blocks. So blocks are the number of uh, tests or samples within each of the treatments, and the depth of those blocks is called J. So J for each one of these treatments doesn't have to be the same. Um, it's easier equation-wise later when they are the same. So next thing that we need to look at is the grand mean is typically written with an X, a bar, and then two dots next to it. So that just means that the I and J are all combined. You're combining all of the values together. The treatment mean here is just going to be within one I, and that's why you have just an I and the dot meaning all of the J's within that I. So to calculate the treatment means, you take the summation of all the points within that I and then divide it by the number of points total within that treatment. For the grand mean, you take all of the points and divide it by the total number of points. Or it might be easier to take the treatment means, add those together, and then divide it by the number of treatments. Now we go to our statistics. We have SSTR, so sum of the square sum of treatments, and one form of that is going to be the depth of each of the treatments times the quantity of the treatment mean minus the grand mean, and that's squared. For SSE, there are typically two equations that we'll use. Uh, the first one is a double summation where you have each individual data point compared to their respective grand or the respective treatment mean. That's squared. Um, I see this as a little bit harder and it's a little bit more tedious. So what I suggest doing is using the second equation here, where you find each of the standard deviations or variances of the treatments and then multiply that by the number of samples within the treatment minus one. It's a little bit quicker and you can use your calculator for finding the variances, and I'll show you that in an example problem. The next part is normalizing the SSTR and SSE. So you have to divide by the degrees of freedom for each of those. For SSTR, it is related to the treatments. So we have I minus one there. For MSE, it is related to the squared sum of errors. So within each data point compared to their treatment, so each data point compared to their treatment, that'll be n minus I. For the f-stat, we have MSTR divided by MSE. And for degrees of freedom, it's our numerator divided by denominator. Oh, that should be an n. So I minus 1 is our numerator, n minus I is our denominator. And then you can use FCDF to find the probability at the end. All right, so let's go to an example problem. So we have 3 different machines are being considered for use in manufacturing rubber seals. Let's count off some of the things that we need here. So here are our 3 treatments or 3 different processes. And then within each treatment, we have 4 samples. So that means each of the J's are going to be the exact same. So first we'll write our null and alternate. For ANOVA, the alternate hypothesis is that, and it's easier just to write this out, at least one mu is different from the others. And that's just meaning that each one of these processes could be so far different from the others that you can't conclude with confidence that uh, one of these populations is different. With the null hypothesis is that all of them are the same. So there's 2 ways to do that. So you can say all populations are the same. You can either write it that way, or you can write it as mu1 is equal to mu2 is equal to mu3. That's just saying that they're all uh, hovering around the same mean. So before we get into the grand mean and all that stuff, the first thing you should do is go to your calculator and input all of the treatments into your lists. So on a calculator, click Stat, Enter, and go to list 1, click down, and now you can start entering your data. Okay, so now once you've entered your data, click Second, and then Mode. And now you're back to the regular screen. So what we are going to need are the means and then the standard deviations. So for the means, you click Second, Stat, click the left button for Math, go down to 3, and we have mean, and click Second, L1 for list 1, and that will get us the mean of our first treatment. So x1 dot, that is equal to 17.2. And we'll do this for the next ones as well. Okay, so now we're here and we can get the standard deviations for each of these. This is in the same place as second stat. Go down to standard deviation, click enter, and then second L1 to get the standard deviation of the first list. Okay, so now that we have all these, we can go and start calculating our statistics. The grand mean is going to be the first thing that we'll calculate. So that's the summation of the treatment means that divided by the number of treatments. So divided by I. Okay, so we have our grand mean there. The next thing that we'll calculate is SSTR. The formula we'll be using for that is the summation for each of these treatments. The JI times XI bar minus the grand mean. That's squared. So what you can do here is input this equation into a list. So we'll put that, so we'll go to lists, go edit, and we need a place to keep all of our XIs. In this case, the L3, L2, and L1, we don't need those anymore. We've already found our statistics, our treatment means and standard deviations from them. So you can clear those. So if you click clear while hovering over, oh no. If you click delete or clear, those will clear those values. So we'll put in our XIs into there. So now we have those. For all of these, our JIs are going to be the same. So hover over list 2, and now we can input our formula into there. Our JI is going to be 4 for all of them, so we'll put in 4. We have to multiply by a quantity, so we'll put in times and then a parenthesis. Our XIs are held in list 1, so we'll hit second 1 to input list 1. Then we have to subtract our grand mean from this, that is 17.517. We'll close the parentheses, and then we have to square this. So now this will auto-populate with those values, but we still need the summation. So click second mode, that'll quit out to the main screen. Second stat, go to math, and you can sum that list. So we put those in list 2. And so we have 2.601. That is our SSTR. So here, I'm going to write for list 1 minus 17.517. This is so then when you're on a test, we can see your process. You're putting your XIs into list 1. For SSE, there are 2 formulas, but we're going to use the formula that uses the standard deviation. So this is JI minus 1 times SI squared. So we'll need to put our standard deviations into the list here. So we'll put that into list 3. Okay, and then in list 4, we'll put in our equation. So JI minus 1. So this is going to be 4 minus 1 times our SI. Our SIs are held in list 3. So we'll parenthesis 4. Oh, it doesn't like that. Parenthesis 4 minus 1. And then times our SI, which is list 3. So second 3. And we have to square those. So now we get a summation here. Or we get our values there. We can go back and then sum these things together. All right, so now we can sum our stuff. We put all of these into list 4, so we'll click second 4 for list 4. And we get 23.53. All right. Now we have to normalize these. So MSTR, that is equal to our SSTR divided by I minus 1. So that is 2.601 divided by I minus 1 is 2. So 2.601 divided by 2. Get 1.3005. MSE is SSE divided by N minus I. So N, we have 4 samples per treatment, 3 treatments. So that is 12 samples total. This will be 23.53 divided by 12 minus I is 3. So we'll divide by 9. So 23.53 divided by 9, 2.614. Next, we have to get our F value. It's going to be MSTR divided by MSE. It's going to be 1.3005 divided by 2.614. So our F stat is equal to 4975. So from here we can use, before that actually, we should get our DOF. So the first one is I minus 1, second one is N minus I. So that is 2 and 9. Then we can get our FCDF of our 4975. So click second and then vars, scroll down to FCDF. So we'll keep our lower number as the same. Our upper number is going to be what we found before. So the 0.4975, put a comma in there. Degrees of freedom for the numerator is I minus 1, that's 2. Degrees of freedom for the denominator is 9. So we'll click enter, we get 0.376. For this problem though, what we need is the right side of the graph, the area to the right side. This calculator, what it did was it gave us the left side. So say this is our graph right here, and then this is our f-stat value. The area that we want is over here, but we just calculated this area. We calculated the orange area just because we started our lower value at 0, and then our upper value was our f-stat. So what we need to do is we need to find the complement of the FCDF. So we have to take 1 minus FCDF. That is our p-value. So p-value that's equal to 1 minus that. So 1 minus 0.376. So p-value is equal to 0.624. So that is way bigger than an alpha of like 0.05, even if you chose 0.5, which wouldn't make any sense. It would fail to reject. So we fail to reject the null since p-value is greater than alpha, meaning there is insufficient evidence that there are these processes, machines are being compared to, oh yeah, so that the machines are different. And that is it. That is your final answer. So I hope this helped you a little bit with the whole process of using your calculator in ANOVA, and I will see you in the next one.